So welcome back to part 2 of chapter 1, where we're going to continue the data analysis of this winter weather in January in Michigan. And we've looked at the data, we've considered the IID situation. If we want to start investigating dependence more, we're going to need a model. And a fundamental class of models is the so-called autoregressive-moving average, or ARMA models. These models are to time series, rather like what the linear model is to standard data analysis. We'll look at ARMA models in much more detail later in the course, but let's start to get acquainted with them. Here's one particular ARMA model we're going to fit. Yn is mu plus alpha, yn minus 1 minus mu plus epsilon n plus beta epsilon n minus 1. So the term alpha yn minus 1 minus mu is called a one lag autoregressive term. One lag because it depends on n minus 1. Autoregressive because y depends on itself at previous lags. And there's also a one lag moving average term, beta epsilon n minus 1. We always have the noise term epsilon n, but then we could have any number of larger lags. So it's called an ARMA 1-1 model, AR1, MA1. If alpha equals beta equals 0, we get back the basic independent model, yn is mu plus epsilon n. If alpha is 0, we have just a moving average model, MA1. If beta is 0, we have an autoregressive model with one lag, AR1. Now, to complete the specification of the model, we need to say what these error terms, epsilon 1 to epsilon n are. They're going to be independent, identically distributed. We could decide they were uncorrelated instead, but to be concrete, they're going to be IID normal distributed with mean 0 and variance sigma squared. A little note on notation. In this course, capital Roman letters X, Y, Z will be random variables. We can also use certain Greek letters, epsilon, eta, psi, zeta, for random noise processes, and these symbols are used to build models. Models are random variables. Lowercase Roman letters denote numbers, not random variables, and Y star in particular is going to commonly be used to denote a data point. It's a little unusual to put the star on data. I like to do it partly following William James's advice. We must be careful not to confuse data with the abstractions we use to analyze them. So putting a clear signal of what is the data has some advantages. So other Greek letters will usually be parameters, which are real numbers that form part of the model. A technique we're going to use a lot in this class, and we'll talk more about later, is maximum likelihood. So we can readily fit the ARMA 1-1 model by maximum likelihood just using an R function. And we're going to be interested later on in learning how R does this. How can you maximize the likelihood? If you want to use statistical methods well, even if a computer does them easily, you have to understand what's going on under the hood, at least enough to be a good user. But for now, let's start off by just doing it and seeing what we get. So ARMA 1-1 gets ARIMA, the data Y low, and the order is C101. The extra 0 is because in general it's an ARIMA. I is for integrated, we'll see that later, but it's got no integration, so it's just ARMA. Then if we want to look at what we've got out, we type print ARMA 1-1 or just ARMA 1-1 in R to give a summary of the fitted model. And alpha is called AR1, beta is called MA1, mu is called intercept in the context of the model we just wrote before. And here is the summary. We see estimates, standard errors. We see an estimate of sigma squared. We see a log likelihood that's been maximized. We see AIC, which many of you will have heard of before. This is Akaiki's information criterion. We're certainly going to talk more about that during the course. Okay, well, let's write the ARMA 1.1 estimate of mu as mu2 hat and its standard error as SE2, and then we can compare those with the mu1 hat and SE1 that we had for the IID model. And this will start getting us a feeling for how important dependence is in this particular model. Okay, before we move further, I'm going to talk a little bit more about investigating R objects. This is involved in the topic of the reproducible computing, knitter, and R Markdown that I mentioned earlier. So if you want the numbers from your data analysis to be entered directly into your report, you shouldn't be cutting and pasting numbers from summaries. You should be extracting them in code from the summary and putting them into your analysis. But it takes some poking around to extract these quantities from the ARMA model in R so that you can then put them into your report in R Markdown. Well, ARMA 1.1 is the fitted model object. It turns out it's an R list. And so to see the components of that list, you type names ARMA 1.1, and then here you see the components, and quite quickly some things come to mind. Well, I bet COEF is the fitted coefficient. I bet log lick is the log likelihood. I bet AIC is Akaiki's information criterion. I bet var.coef is either variance matrix or a vector of variances for the coefficients. Okay, so then we can go ahead and investigate those things. And we'll find fairly quickly that if we do ARMA 1.1 COEF intercept, we pick out the estimate of the mean from that model. And if we look at the intercept and if we look at the intercept component of the matrix, the covariance matrix associated with ARMA 1.1, and we take its square root, then we get SE2. We can check that we've done that right because they should match what we got from the automatic printout. And so there we are, we have mu2 and SE2, but now we have them in a form that can be plugged into the report. Now we can compare the IID estimate with the ARMA estimate. One thing we see is that the estimates mu1 hat and mu2 hat are really very close. They only differ a little bit in the third significant figure. However, the standard errors differ in the first significant figure. So SE1 is 0.68. This is an underestimate of the error compared to what we think is probably going to be the better estimate, SE2 of 0.81. And so the naive standard error in this case is about 20% too small. Well, 20% isn't a huge amount, but it's enough that you can, if you don't account for that extra uncertainty, then you'll get quite a few hypotheses that could be explained by random noise, but seem clearly significant with the shrunk standard errors. Okay, so the details underlying this ARMA 1.1 analysis will be covered later. But one thing that we can just think about a little bit now is how do we even know if the ARMA analysis is more trustworthy? It's a more complicated model. Being complicated isn't always good. So, well, this is really a general statistical question. How do you know if one statistical model is better than another? You can maybe, you could compare AIC values. You could say, make a likelihood ratio test, or you could say look at residual diagnostics. Those are all good things to do in general, and we can think about how to do them specifically in the context of time series analysis. Well, really, perhaps the first thing to do is to look at the residuals. Then we have to decide what the residuals mean for an ARMA model. We know what they mean for linear regression, and we know that looking at residuals is a good thing to do in linear regression analysis. And it's a good general principle that if you know something for linear regression analysis, you can extend it to ARMA analysis. Okay, so for an ARMA model, the residual Rn at time Tn is defined to be the difference between the data Yn star and a one-step ahead prediction of the data based on the data up to time n-1. We call this YNP, P for prediction at time n. Now, how are we going to do this? We have the ARMA definition, which I've copied again here in equation 3. And if we want to predict Yn from the previous data, we might think, well, we know that the epsilon n's are mean 0. We can't really predict them. Let's just plug in 0 for those things, and then we'd get a prediction estimate. YNP is mu hat plus alpha hat, Yn-1 star minus mu hat. And then a residual time series would have its nth entry, which is just the difference between Yn star and Ynp. I'm not starring R, so this is this little star should really be crossed out. There we go. So there are more sophisticated ways to define residuals, and actually R does something slightly more sophisticated, but it's essentially this. And now we can look at these residuals. ARMA $1 resid gives you the residuals, and then you just plot them and you see what you get. So we still see slow variation in the residuals over a decadal timescale, but the residuals look fairly close to uncorrelated. How do we quantify this? Well, we quantify correlation by sample correlations, but when we do time series analysis, we often look at something called the sample autocorrelation function, or sample ACF, which is defined in this case to be the correlation between lags separated by h for all h, and the numerator looks very much like a covariance estimator. The denominator looks very much like a variance estimator that scales to make a correlation. One small difference is that note we use 1 over n, not 1 over n minus h, or even 1 over n minus h minus 1, you might think from the standard correlation estimates. but we'll find out why we do that. Well, the short answer is it gives more stable estimates for larger values of h, when if you did 1 over n minus h, you'd get a more unstable estimate. Okay, so here is this sample autocorrelation plot, and this shows no substantial correlation. The ACF is always 1 at lag 0, and let's say under null hypothesis of no correlation, blue lines, are a 95% region for the sample. Autocorrelation. So here, if it's a test at a 5% level that the sample autocorrelation leaves this region, if you do 20, you'd expect maybe 1 to be just outside the region. That's what happens in this case. So we conclude there's no substantial autocorrelation. This could mean an ARMA model is not a good way to describe the variation. When you look at the residuals, you see this sort of small indication of slow variation, but maybe an ARMA 1.1 model can't capture that. This is a simple example, but the general topic of inadequate models giving poor statistical uncertainty estimates is a general concern when working with time series analysis. And let's think about this at a sort of higher, more general level. Usually, omitting dependence in the model will give overconfident standard errors. That's certainly what we saw in this case, and that leads to scientific reproducibility problems because chance variation is too often assigned statistical significance. Beyond scientific applications, it can also lead to improper pricing of risk in financial markets. And in fact, a large factor in the US financial crisis of 2007, 2008 was failure to acknowledge dependence between risk in investments. Okay, here's a little summary of the second part of the course that we're heading towards, state space models. So scientists and engineers often have equations in mind to describe a system they're interested in. Oftentimes you have a model that describes the dynamics of the system and another model that describes how you can measure it. The measurements are often imperfect and noisy. Sometimes there are variables that you can't measure. And when you put all this together, it's called a state space model. And we're going to spend half the course on these things. The state models, the quantities that we think determine how the system changes with time. And these idealized state variables are often not directly or ideally measurable. And so statisticians have a task to help scientists choose between rival hypotheses and estimate unknown parameters in the model equations. And again, there are many scientific applications. The model may be linear, nonlinear, Gaussian, non-Gaussian. We want to be able to deal with all those possibilities. Here's just one example from finance fitting a model of volatility for a stock market index. So suppose our data are the daily returns on the stock market index. In this case, there'll be the Standard & Poor 500 index. Well, what's a return? The return is the technical term for the difference of the log of the index. So if Zn is the actual raw S&P 500 index for day n, then Yn star is log Zn minus log Zn minus 1. You might think that the holy grail of finance was to predict the stock market, but the stock market's notoriously unpredictable. And so a more practical and practically more important thing is often to not try to predict the stock market, but to understand the risk of the stock market. And so that risk, the variability of the returns, is known as the volatility. And that's fundamental for both assessing the risk of financial investments and also assessing the price of financial tools to help buy and sell risk. Now we come to a model. When you're working in a domain, the people who spend all their time thinking about that domain in terms of finance, right? You have financial engineers, financial mathematicians. They develop models. As a statistician, you may have the task of investigating a model that somebody else has proposed. At least when you start working with the model, it can look kind of large, complicated, confusing. You may not understand it yet. But the point right now isn't so much to understand this model as just to look at the sort of models that get proposed. Okay, so investigators develop models for how dynamic systems progress through time. And here is one. So Yn is modeling the returns, the e to the hn over 2 is the volatility, and then the volatility itself in this formulation follows an equation which has an autoregressive character. It has a dependence on the previous data. It has a dependence on this slowly varying process Gn, and you have to think why this should be an equation of interest, but let's trust the financial mathematicians on that. And we're postulating that epsilon n is normal 0, 1. The other driving noise processes are IID normal, and H, the volatility, is unobserved, but the return modeled by Yn is observed. Okay, so we can just think of this as an example of a mechanistic model that any statistician can try and sink their teeth into. We're going to want to estimate the parameters such as mu h, phi, sigma nu, sigma omega. We want uncertainties on those parameters. We want to know if this model fits better than alternative models. And so far as it does, we want to be able to talk about what we've learned. Maybe the model won't fit so well, or maybe it'll fit some things well and not things others. So maybe we'll learn something without concluding that the model is also good. Okay, so likelihood-based inference for such partially observed stochastic dynamic systems are possible and can be used to address these questions. This particular analysis comes from Bretto 2014, but you don't need to follow that reference now. But by the end of this course, you'll be able to carry out data analysis of this type. And if you want some examples to motivate you as you go through the course, stick with the course, and you'll get to the point of doing final projects comparable to ones that have been done in the past. And there are links here to the 2016, 2018, 2020 final projects posted on their respective GitHub sites. And that's the end of chapter 1. Thank you.